Hello, Professor.
Hello, everyone. How are you?
Good. I had a quick question.
Yes.
Um, on like what are the homework? What's this equation? It said V naught x equals V naught squared minus V naught squared y. What equation is that? I don't because I don't really remember learning that equation, but it was used on like you posted the homework solution
Uh-huh.
and yeah,
So
that equation was there.
question 13 or 14?
Uh 14.
Oh, 14 or 15? 14. Okay, let me see which one you're talking. Okay, say, oh, so you're saying V naught x is equal to square root of V naught squared minus V naught y squared?
Yeah, is that like is it because the Pythagorean theorem there?
Yes, because V naught squared is the x component squared plus the y component squared. So if you want to know one of the component, that's what you would do, right?
Oh, okay, I get it. Thank you.
Sure. Yes, so these two problems, question 15 is a little bit complicated, but it's not difficult. It's really just they give you some information, and then you just have to use that information to figure out, for example, h minus that big H minus little h. It turned out you don't have to solve each one of them individually. You can replace h minus little h with the L in your equation. So there are just some substitution required. So with my solution, you can plug in the numbers that your problem has, and I believe that you will be able to figure it out.
Do we have to use like arc cosine for that one?
That one, yes. The one that how I solved it, I found it's easier to find t first. And then with the t, you've got two different values for t. You can find different cosine value, and that give you two different angles.
Okay, thank you.
Sure. And thank you for asking that. Okay, so let me go ahead. I believe my screen is shared. We will talk about circular motion today, and at the end of the circular motion, there's a question that can help us transition to talking about Newton's first law, and we will continue with the discussion of Newton's laws of motion for the rest of next week. So let's start with circular motion. We're gonna take a look at this question first. Let's say if you have a car it's going around in the circle. While going around, the speed is constant. Let's say going around in the circle in 20 miles per hour per second. At this particular instant, do you think there is any acceleration on the car as it going around the circle? So here is just a quick vote on this question. All right, 10 more seconds. Let's still vote for 10 more seconds. Okay, any other last minute vote? Okay, if not, let's go ahead and end this. So we'll take a look at the results. All right, so the car speed is constant, do we still have an acceleration as it's going around the circle? What do you think?
I think that because acceleration is just simply a change in velocity, the actual direction of the velocity is always changing based on the circular movement. So there's got to be an acceleration of some sort. It just has to be that the overall, the magnitude of the velocity ends up staying the same.
Very good, thank you, Juan. The acceleration is defined to be the change of velocity over time. So as long as there's still a change, there's going to be a velocity, right? So even if the speed is the same, the direction of velocity is still changing. So that definitely requires the acceleration, right, to change the direction. So direction is changing. So there must be a net acceleration, right? So the direction of an object is always tangential to the curve, right? So at this point, the direction this way, at this point, the direction is this way. And you can see that this direction is always changing. So therefore you must have an acceleration. Excellent, thank you so much for the thought. So let's take a look at the direction of the velocity, also derive the magnitude of this acceleration. This have already been in your pre-lecture, you have seen this already. So if we look at two different instants that's very close to each other, right? V at time t and t plus dt, that's a very short amount of time right after this instant. If you look at the change in velocity, this delta v is always pointing toward the center. So that's why the acceleration is always pointing toward the center. I will give it a name called centripetal acceleration because this A is always points toward the center. And in terms of the magnitude, they first used a small angle approximation to get the dv, the delta v, little change of dv. So you can see that if we have two vectors, one of them is your velocity at the initial instant, and then your velocity at the next instant, right next, right? After a short amount of time. And you can see the change, delta v, is velocity at a later time minus the velocity at an earlier time. So you can see that the delta v change, little change, is represented by this red arrow because the head-to-tail method shows dv plus v at the beginning of the instant gives me the velocity at a later time. So that is from the head-to-tail method. So we can see that this little short red arrow represents the delta v, the change of velocity that we want. And then we use the small angle approximation. Well, we say that delta v is pointing always perpendicular to the center. This is a right triangle here. For a small angle, we know that sine of an angle is approximately equal to the angle itself in terms of the radians of that number. So sine of this is dv over v, the hypotenuse, okay? Now because the v is right next to each other, there is very little change in the velocity because it's basically an infinitesimal amount of time passed by. So we can rewrite this v at a later time simply using v to represent it because there has been very small change. So overall, you can see this is your small angle, this is your small velocity, dv is v d theta. Okay, so that's why we got this relationship. Having this relationship, we can use that to derive what is your acceleration. So let's go down to see the next slide. So your acceleration, as our definition says, here I'm just going to say the magnitude, okay? I'm not putting a little arrow on it. So the magnitude is dv over dt, right? This is our definition. And dv you have already derived, right? dv is v d theta over dt. So it turned out d theta over dt also has a physical meaning. We now give it a new physical quantity to say what is d theta over dt. So d theta over dt is the change of the angle over time, right? So if you are saying, I'm sweeping around 90 degrees per second, that tells you how fast the angle changes, right? So the angle represents how far you are away from your initial position. So 90 degrees per second, or 30 degrees per second, or 180 degrees per second. So omega represents the rate at which the angle changes. So we're not going to go into more detail here, but later on when we do rotational kinematics, we will go over the omega again. But just here, we all need to know this is called the angular velocity. So it is how fast the angle changes over time, right? As opposed to how fast your distance change over time. That's your linear velocity, right? 5 meters per second. Here is 90 degrees per second. So that is your angular velocity omega. Having that, you can rewrite your d theta over dt using omega. So that becomes v omega. Okay, but there is one more condition, that your linear velocity and your angular velocity are represented by radius r. Okay, so how do we know that? Here we can get this information using a simple ratio relationship. So let's say if you go all the way around, then the distance you traveled is the circumference of the circle. What is the circumference of the circle with radius r? So it's going to be 2 pi r, right? So the distance you traveled going all the way around is 2 pi r. And in the total amount of t, okay? So that is your velocity, right? And in terms of omega is, okay, going all the way around, what is the angle that you traveled? That is 2 pi, right? That is 360 degrees. So that's 2 pi in the same amount of time, right? So you can see from this relationship, you know, v is omega times r. Okay, so which means we can write our acceleration either using v or omega, doesn't matter because they are related. So if we use v, omega becomes v over r. So it becomes v squared over the radius r. Or if you use right omega, it becomes omega squared times r. So your centripetal acceleration, here we have defined the centripetal acceleration is velocity squared over r. Or you can write it using omega squared times r. So either way is fine. Okay, so that is the magnitude of an object going around in the circle with a constant speed. The acceleration is your speed squared over radius. Okay, so this is just a quick summary of the two relationships we have derived. The name centripetal acceleration comes from the effect that the acceleration is always pointing toward the center. So we call this the centripetal acceleration. It's not a new acceleration. It's really just because this acceleration is pointing toward the center, which is also, you can see it's perpendicular, always perpendicular to your velocity. Okay, so this is something we have derived. This is only responsible for what? Only for changing this direction. This is only for changing the direction of your velocity. Okay. So when your acceleration is perpendicular to your velocity, it's not going to make it speed up or slowing down, which makes sense, right? Because if you want to make something speeding up or slowing down, you have to give an acceleration either in the direction of the velocity or opposite of the direction of your velocity. This acceleration is in neither of those directions. It's perpendicular to the velocity. So all it can do is to change the direction of velocity, but not to speed it up or slowing it down. If you do need to speed up and slow it down, you need another acceleration. Okay, and we call that the tangential acceleration, but we don't have to worry too much about this at this point. Knowing that if you want something to slow down, you need an acceleration to be opposite to your velocity. And if you want it to be curling around as well, you need the centripetal acceleration. You will need both of them. Now, in reality, it's not like you exert separate accelerations. You will have an overall acceleration that at the same time change your direction where you're going, also speeding up or slowing down. Kind of like when you're driving your car around the curve, not only you're turning, but you may also be slowing down at the same time or speeding up, right? So you need your acceleration to be doing two things. So in this case, for example, you have an object that's moving along a circular path, but at the same time it's slowing down, right? It's from V1 to V2, the length of your vector is shorter, meaning that the magnitude of your velocity becomes smaller now. So which one of these arrow will represent your acceleration at point X, okay? So here are multiple ways to look at it. The diagram I draw here is one way to look at it is by looking at the acceleration using the change of velocity. But there are another way to look at it. So I want to give you guys a couple minutes to think about this. And when we come back, we can have a discussion together on how do we go about figuring out the direction of your acceleration. So take a screenshot of this picture, and we can have a discussion in breakout rooms for a couple minutes. Okay, so whenever you're ready, you could accept the invitation for breakout rooms.
Professor, could you
yes.
Could you scroll up to the previous slide for a second, please?
Yes.
Thank you. Okay, I got it. Thank you.
Sure.
King D, maybe? Yeah. The reason why I say that is because how the vectors are changing, it's the direction in which the vector is.
Professor,
Yes.
I have a question. For acceleration, in regards to velocity, acceleration would always point to the center of the circle, right? No matter the magnitude of velocity.
Always point toward the center of the circle.
Or basically perpendicular to the velocity.
Only
no matter
change the direction. Sorry, what were you saying?
Sorry, I think I was talking at the same time you were talking. So in finding the acceleration, regardless of the magnitude of the velocity vector, the acceleration vector will always be perpendicular.
No, only when this acceleration is changing the direction of velocity, but not the magnitude. If this acceleration is changing both the direction and the magnitude of velocity, then it cannot be 100% perpendicular. Okay. So my question, my point is, if your speed is constant, then yes, your acceleration will be perpendicular to your velocity. But if you are not a constant speed, then the acceleration will not be perpendicular.
Okay.
Yeah, which is the case here.
Okay, thank you.
Sure. Okay, any other votes on this? Let's take a look at our result. Okay. So we have more of the votes toward it's not perpendicular to the center. Perpendicular to the center would be vector E, right? So A and D seem to get more votes. So we all agree that there has to be another component. So there are two ways to do this. So one way is to look at, okay, you gave me two vectors, and I can always use the two velocity vectors to find the change. And the change is acceleration, right? So you can see that the problem gives you two vectors, velocity at an earlier time, v1, and you move that parallelly to wherever you are doing your work is v1 here. You give you another velocity at a later time, v2, and then move it to where you wanted to do the vector addition, v2 here. You can see these are parallel, right? I haven't really changed either the direction or the length. Simply I'm moving it around. So to do v2 minus v1 is velocity later time minus velocity at early time give you the change of velocity, right? So I need to use this arrow to minus the other arrow. So to do something minus something, we can change it to v2 plus the negative of v1, right? We want to switch it to addition, vector addition, because that's what we know how to do. So v1 is pointing this way, v1 minus v1 is the same magnitude, but flipped in the opposite direction. So you can see this is your negative v1. It's the same arrow, but just flip directions, right? So now you have v2 plus negative v1. You use a head to tail method to add them up, right? These two add up to be represented by this red arrow right here. So delta V is the change in velocity. Okay, so to find out the acceleration at this point, we want to find a velocity before that point and a velocity at that point, right? So that represents, okay, from here to here, I have a change. The change is in this direction. That means that your acceleration is also in that direction. So you can see it's diagonally downward to the left side. So D seems to best represent that result. So that's one way to do this. There's another way to do this, is to look at the effectiveness that you want to achieve. So anybody else use another way to figure out the direction of your acceleration that's different than the one I showed here?
I kind of used a visual approach just because I saw what you did and I kind of thought of something that maybe like wasn't really reliant on physics really.
Okay.
And I kind of just started eliminating ideas. So B I eliminated because the acceleration vector always has to point towards the center. And that one's pointing to somewhere else that's not the center of the circle.
Oh, okay.
C, for the same reason, because if it's going straight down from X, that would not ever hit the center of the circle. A, honestly, the picture kind of looks like A is not, like point X is not like on a unit circle. I don't think it would be 1, 0. I think it would be somewhat above, like its radian measure would be somewhere between 0 and pi over 4. That's how it looks like to me, at least. So basically,
pi over 4, the position of X, you said?
Yeah, the angle of X relative to the center, it doesn't look like it's 0. And from the picture, it doesn't look like it's pi over 2. So I know it has to be somewhere between those radian measures. So then because of that, I know it can't be A and I know it can't be E because either of those wouldn't point to the center. So that's how I narrowed it down to D.
All right, so let's try to complete this path. Maybe that would make it a little more clear. So if we sort of try to complete this path, we will have something like this, right? What happens if the acceleration is directly toward the center? Like what if it is you have an acceleration directly in this way? So
the velocity doesn't change?
Yeah, the velocity will change its direction only, right? So this one is responsible to change directions. But at the same time, you can see your velocity is becoming smaller. One, that what you said earlier was one, right? You said the different method you use.
Yeah.
Eliminating wrong results is simply a very good method in answering these type of questions. So so we eliminated B because pointing away from the center, right? If you have an acceleration in that way, your car probably start going that way. So that's not right. And E is the green arrow I just showed here. If you only have E, then you will only change your direction. You will not speed up or slowing down. But we know it is slowing down. Right now, it is getting have a smaller velocity, right? So here, your velocity would be tangential to your path. So this will be your velocity at that moment. You want it to be smaller. You want it to slow down. So what kind of acceleration could slow it down? You need an acceleration that is opposite to your velocity. You need an acceleration that is in the opposite direction. So if you were to choose C, this is only to slow it down, but not to change directions. So E change directions only, C will slow it down. But at the same time, it's slowing down as it's also changing direction. So you need E and C combined. You need both of those acceleration. You can see that if you have an acceleration inward, you have an acceleration downward. So overall, your acceleration should be diagonally downward to the left. So that is D, right? So that's another way to look at this is what effect are you trying to achieve? Any questions here? Any questions about this?
Professor?
Problem? Yes?
So if we were accelerating, then it would be A, right?
Yes. So if this is longer, then you would choose A. Yes.
Okay. Thank you.
Very good. Yes.
Could you re-explain the first? That was the second method. Could you re-explain your first method?
My first method is take these two vectors, V2 and V1, and directly using V2 minus V1 to see what is delta V. Delta V is in the same direction as acceleration. So here I did a vector addition between V2 and negative V1. I see that my delta V is the change of velocity is downward diagonally to the left. So I choose D, which is the direction of the acceleration, right?
For that method to work, Professor, do we need V1 and V2 to be equidistant from X?
It doesn't have to be exactly,
Okay.
because we are really just choosing a general direction. So nobody is saying D is exactly 40 degrees down that way. So you're only choosing, it's in that direction. It could be up a little, down a little. You don't have to be exact. That's why we don't need to be equal distance from X. Any other questions?
So then if this is the approach to finding the acceleration, how would it look if it was decelerating?
It is decelerating. At this question right now, it is decelerating because you can see V1 is a longer arrow than V2. So think about this as your car turning. As you are turning, you're also slowing down. So it is decelerating. Does that make sense?
Oh, right, because yeah, there is a change in direction. Oh, okay, thank you.
So two methods. One is to find delta V, and A is the same direction as your delta V. The second method is to find the two effects. One is to change directions. One is to speeding up or slowing down. Change direction of your velocity plus speed up or slowing down. So in this case, we're slowing down. So both of those methods will give you the same result. All right, so let's look at this bridge question you have done already on your pre-lecture. Let's say you're turning around a rock and tie a rock to a string. You can kind of swing it around in the horizontal circle. If the string breaks at this instant, which path do you think the rock would follow? Noting that we are looking at the top view, okay? So that might also change the result. If you look at a different perspective, you would draw it a little bit differently. So here we're looking at simply from the top view. So from the top view, we know that in real life, we know that which the rock will go, right? We'll kind of flying, it's like it has this horizontal velocity, but at the same time, you have gravity pulling it down. So it's kind of just gonna fall down that way. So in the parabolic curve. But if you're looking at from the perspective of the top view, you don't really see the falling down because you're looking down, right? You only see that it's changing in the horizontal direction. So that path is best represented by choice C. So the idea of this question is really to show us a connection to our next topic, is that when you don't have that acceleration, right? So the rock of the velocity at this instant is in this direction, tangential to the path. If you continue to have this strain, which means the strain will try to pull it toward the center. So, right, the rock will continue to curling around. Without that velocity, it's not going to curl around. Here, if you continue to pull it toward the center, it's going to continue to change its direction of your velocity. But if your strain breaks, it's not going to come closer. It's not going to turn, right? We're not going to be able to turn. So what it will do, the horizontal velocity will just remain that velocity in the next parabolic motion. So this horizontal velocity will not change, will remain that same magnitude and same direction as if flying away, right? So it's going to fall down, but the horizontal velocity is still the same magnitude and direction. This brings up to our next topic is An object, if it's originally at rest or if it's already in motion, it will stay in the same motion, either stay at rest or stay in the same motion with that same speed and same direction, unless you have an unbalanced force acting on it. So this is called Newton's first law. A lot of times in the past, especially in history, people have used inertia to represent this phenomenon, but that's an outdated word. That is inertia. I'm sure that we have already all heard of that word before, right? So in your opinion, what does it mean to you when you hear the word inertia?
The ability of something to the ability of something to resist a change in motion.
Yeah.
Velocity.
Yeah, so the word inertia seems to think that you have an ability to remain that same speed and same direction, remain that status of motion. But Newton's first law is really saying that it's not really you have some special, it's not really a special ability. If you're remaining the same speed and direction simply because there is a lacking of a force acting on you. So without the force, of course, there's no reason to change, right? So it's not really something special about the feature of inertia. It's really just whether you have a force on it. So that's why we are trying to get away with using inertia to represent explain phenomena. For example, if I say, okay, you're driving a car, right? Really, really fast, and all of a sudden you hit your brake. And what do you notice about yourself? What do you tend to do if you hit your brake really hard?
Your body moves forward a little bit.
Yeah, your body moves forward a little bit. So you might want, without learning Newton's first law, you might answer, how do you explain to people why your body moves forward?
Because that's essentially the unbalanced force. Like you're approaching at a constant velocity, and then all of a sudden you brake hard, which you're like, in other words, like effectively interrupting that constant velocity.
Yeah, so you're trying to use Newton's first law. Very good. Without learning Newton's first law, we might simply say, oh, that's your inertia. Your inertia is still maintaining that same speed of going forward. But with now learning Newton's first law, you will simply say, well, of course you would remain that speed and direction, but now hitting the brakes, there is a force acting on you trying to slow you down. But it will take some time for that force to completely slow you down. So that's why during that, the car slowed down first, and you slow down because you are strapped in and you're sitting on the seat. So all of that straps, belts, and seat will exert force on you to also slow you down. And it will take some time for that force to change your status of motion, right? So that's why you're seeing yourself still relative to the car still moving forward, because the car has already slowed down and you haven't. That's why it looks like you are slowing, you are moving ahead of the car at that moment. Okay, so all I'm saying is we try to stay away from using the word inertia. Now we already know Newton's laws. Okay, so the second big topic of Newtonian mechanics of the semester is first we studied motion. We looked at position, displacement, velocity, acceleration, right? And then we're going to look at the forces which is responsible for any changes in motion. So we're relating the forces and the motion together. This is what we're going to do in dynamics. We use the force a lot in our daily language. And if you ever need to give a specific definition for force, so what is a force? You might say a force is a push or a pull. That's perfectly fine. But in physics, we describe force as a type of interactions. So in nature, in the universe that we live in, there are really only 4 fundamental type of interactions. All of the different forces can be put into one of these 4 categories. The first category is gravitational interaction, or we can call it gravitational force. These type of forces are responsible for us feeling gravity on Earth, gravity that is responsible for the motion of our planet around the sun, and the motion of the other planet around the sun, motion of one galaxy and another. So that's all gravitational interactions. And the second type is very common in our daily life, electromagnetic interaction. So magnets, electricity, all of these devices we use in our house, it's all electromagnetic interaction, radios, waves, and your internet connection. The third type is a strong interaction, strong force. These are responsible for holding the atoms together, and the nuclei, the forces within the nuclei. And the weak interaction, the very last type, is radioactive, responsible for radioactive decay of the element. So it's either one of those 4 interactions that we deal with in our universe. So so let's go through the forces we are going to be talking about in this semester. The first one is gravity. Is always pointing down. So on Earth, the direction of the gravity is always downward. So it's only long range force we will deal with in this semester. So what I mean by long range is acting without direct contact with each other, right? So let's say if you push or pull something, you need to have a contact with the object. Later on, the next forces, friction, normal force, all of those require contact. But gravity doesn't, right? You don't have to touch the Earth to feel this force. For example, apple falls from the tree because the force is acting on the apple. There's a pull from the Earth directly downward. It does not require a contact with the Earth. So the label, we use force with a subscript G, meaning the gravitational force, to represent this. Or a lot of times people use weight, W, to represent it, because that is exactly our weight. So if we say the weight of your weight is 120 pounds, for example, that means the gravity pulls on you for 120 pounds. That is the magnitude of that. The second type of force we will do a lot in this semester is called the normal force. So it's a contact force require you have contact with the object. So it simply is a supporting force. Normal force is a supporting force. When something pushes on the surface will support you with the force upward. So it's always perpendicular, or we say normal. Normal to what? Normal to the surface. If you have a frog now sitting on the surface is providing a normal force on the frog, which is pointing directly upward and perpendicular to that surface, right? So if the surface is flat, let's say you put your book on the table, the book is providing a normal force straight upward on the book. Now, if you tilt your table a little and your book is still at rest, right? And then normal force is also tilted because it's always perpendicular to the surface. And you can use F of N, the normal force, to represent it, or the capital letter N, simply representing the normal force. The third type is friction. There are two kinds of friction. One is a static friction. So static friction really just prevents slipping. So again, the frog is sitting at rest on the surface. So if your surface is lack of friction, which means if it's very slippery, the frog will slide down, right? But it's not sliding down. So to prevent slipping, there must be a friction pointing upward along the surface. So friction is always along the direction parallel to your surface. So in this case, static friction is pointing upward, up the ramp. You can use F, little s to represent it, showing it is static friction. Now, if something is moving, like you're sliding across the surface, sliding across the snow or going across the room, then you have kinetic friction. Now it is moving, right? Object is moving. Kinetic friction is always opposing the direction of your velocity. So if you're going to the right, the kinetic friction is pointing to the left. So you use little f of k to represent it. Now, sometimes if you only have one friction in the problem, you don't have to specify it as a static or kinetic. You can just say little f or the force of friction as a subscript to represent that friction. But if you have two kinds of friction, then you do want to differentiate. Two will not all coexist at the same time, but let's say one scenario, we have a static, another scenario has friction. You probably wanted to put different labels on them so we don't get confused. One second to last force is a spring force. We know that when you compress the spring, it's going to push you, right? If you drag the spring, stretch the spring, it's going to pull you, right? So spring force can also push or pull, and we simply represent it using F of spring to show that is a spring force. We'll talk more about how to calculate the spring force later on, but at this point, we all need to know that there is a force from the spring. The longer that you stretch it, the bigger the force is going to be, right? That makes sense. Last force is force from a rope. We call it tension. If you're dragging a rope, then there is a force, there's a tension everywhere inside the rope. Meaning that if you are, two people are pulling on the two ends of the rope, right? So everywhere inside is going to be the same tension throughout. If you have a tension on the left-hand side, it's the same tension on the right-hand side. This is for a rope that cannot be extended. It's not like a bungee rope. So it's for the rope that we use in our problems. It's all, we assume an ideal rope that cannot be sort of stretched out. Okay. So tension is everywhere inside the rope. So the symbols is simply T, tension, or F of T as a subscript. So you can choose whichever symbol that you want to use. Okay. So here's a summary of all the forces. In our next week of discussions, we will continue to discussion of the forces and how do we combine all the forces to analyze the motion of an object. So you got gravity, you got tension, normal force, friction, and spring force. So those are 5 types of forces we will be dealing with in this course. Okay, right? So that's all for today. I will see you guys next Monday, and have a good rest of the week. Have a good weekend.
I have a quick question. What did you say about like not thinking about inertia again? Because I remember when I learned physics, like we always talked about inertia. Well, you told us like don't think inertia for one thing earlier.
Inertia is an outdated word. We can't explain the phenomenon simply using Newton's laws. So my point is, let's say that you hit your car's brakes and your body gets thrown forward. Yeah. So your old way of explaining this might be, oh, that's your inertia. But we don't have to, but that makes it sound like you have this special feature called inertia. Inertia is not something you can measure. It's not a measurable quantity. That's why we say it's outdated. It's not an actual physical property. However, what you can measure is your speed, is your acceleration, and is your force. Those are the things we can measure. So instead of saying that your inertia is the one that makes you move forward, you're saying, well, both your car and you will maintain that same velocity unless there's another force acting on it. When you hit the brake of the car suddenly changed the car's motion. The car is now slowing down. But the force from the belt and the force from your cushion of the seat hasn't quite changed your motion yet. It takes some time. Like I said, it takes another 2 seconds to change it. So of course, you're still remaining that same motion compared to the car. So the car has already slowed down, but you haven't. So that looks as if you've been flowing forward. So you can explain it this way instead of using inertia to explain it.
Oh, okay. I see.
Yeah.
And sorry, last thing.
It's not something we can measure.
Okay, I see. And last thing is, let's say we drop two things, right? At the same thing, like heavier and lighter, right? Shouldn't the heavier hit the ground first because like its gravitational force would be higher?
That's a great question. We will get to that. It will have a bigger gravitational force, but at the same time, it is also bigger. It also has a bigger mass. So if you look at the acceleration, that effect cancels, give you the same acceleration. It's like okay, how if you have a smaller ball, a smaller object and a bigger object, one has a smaller mass, one has a bigger mass.
Yeah.
To make them move at the same rate, the bigger mass will require a bigger force, right?
Yeah.
So sort of that bigger force and the bigger mass, the effect cancel each other so that eventually they all still move with the same acceleration.
Also, no matter how heavy or light something is, they'll fall at the same time.
They
regardless.
would. They
Okay.
would. But in real life, you often observe something different because they still have air resistance.
Oh, yeah. I see. Thank you so much, Professor.
Of course.
Professor, have a good weekend.
Have a good weekend yourself. Thank you. Bye, everyone.